my name's Tim Dignan. I'm a researcher here at UQ, and I want to tell you today about an interesting puzzle, which I think I've explained. So this is actually a nice example of an experiment you can do at home in your kitchen. All you need is a soda stream. And the basic idea is if you've had a soda stream, you know what it looks like when you put the bubbles through. Bubbles rapidly merge and coalesce and rise out of solution, and you end up with something that looks just like pure water almost immediately afterwards. Interestingly, what you end up with when you add salt water to your solution is something really quite different. And you can see that here is that at first it looks similar, but later on you can see if it zooms in a bit that it's actually quite cloudy. And that's because there are a large number of small bubbles suspended in solution that rise much more slowly to the surface. And this is a phenomenon known as bubble-bubble coalescence inhibition. The basic idea is that the bubbles aren't merging together to form larger bubbles and rise out of solution, so you end up with a lot of small bubbles that rise much more slowly. And this is the explanation for why, or part of the explanation for why, the ocean appears more foamy than fresh water. And it's also has some quite important practical applications. It can be used for mineral extraction and potentially for desalination and some other exciting things as well. And that's mainly because you get a much larger surface area of your bubbles in contact with your solution because they're so much smaller. Now, remarkably, we still don't actually fully understand what's going on with this phenomenon. So the original explanation for this goes back to the 1970s and was put forward by a researcher named Marucci. And what he did was he tried to explain this in terms of one of the most basic and fundamental properties of electrolyte solutions. And that is, we know if we add something like sodium chloride to solution, these ions will be repelled from the air-water surface. That's because they have an image charge repulsion. They like to interact with the water. And this effect will cause an increase in surface tension as a function of concentration of added salt. This is well known. And that's due to the Gibbs adsorption isotherm. And so what Marucci said was, well, let's think about what happens as two bubbles come together and coalesce or merge. And the basic idea is that as they come together, a thin film between the bubbles will form, and that thin film of liquid will need to drain before the bubbles can coalesce or merge to form one larger bubble. And as this thin film drains, what Marucci pointed out was that there will actually be an increase in concentration of ions in this thin film. And that's because a significant proportion of this thin film is actually the surface region. And in that surface region, we know that the ions are depleted, and therefore less ions will be coming out of that thin film than the bulk concentration. So the concentration in this thin film will gradually increase. And this increased concentration will then lead to an increased surface tension, because as we know, higher concentrations of salt has higher surface tensions. And so now we have a thin film with a higher surface tension than the rest of the bubble. And so this will actually arrest or stop the drainage of this thin film due to the Marangoni effect, which describes what will occur when you have surface tension differences on a surface. And so this is quite nice. Marucci derived some equations to describe this and showed that the surface tension of electrolyte solutions was plausible in size in order to explain this phenomena quite nicely. Another really interesting thing, though, that he pointed out was that you'll actually get this exact same phenomena for solutes, ions, that are accumulated or enhanced at the interface. And that's quite counterintuitive because we know that for ions that are enhanced at the interface, they will actually decrease the surface tension of our electrolyte solution, again, according to the Gibbs adsorption isotherm. So you'd expect the opposite phenomena to occur. But what he pointed out was that, in fact, for these surface accumulated ions, your concentration in the thin film will actually be less than bulk. And that's because you have more ions at the surface making up a significant proportion of this thin film, meaning more ions are leaving the thin film than the bulk concentration, decreasing the concentration of ions in that thin film. And then again, this will lead to a surface tension increase because now you have a lower concentration leading to a higher surface tension. And therefore, exactly the same effect will occur. And this is called the Gibbs-Marangoni stress, or Gibbs-Marangoni pressure, some people call it. And so this is a very interesting phenomenon. You get both the same effect for surface enhanced and surface depleted ions. Now, not everyone agrees that this is the correct explanation for this bubble-bubble coalescence inhibition phenomena I talked about. And there are a few reasons for that. One is that it doesn't have perfect experimental agreement. Things like the dependence on bubble radius may not be so perfect. But I think this is mainly attributable to inaccurate parameters being put into the model, parameters not be fully characterized. Also, there may be some other contributing forces which aren't fully taken into account in the model as well. Things like a hydrophobic attraction, for example. But there's some really good reasons to think that this model is really accurate. And so Liu et al. In a preprint have a really nice demonstration. They show that this basically generalization of this Marucci mechanism can actually explain quantitatively the film thickness as a function of time really nicely if you look at these two bubbles coming together. It also explains why the transition concentration, that is the amount of salt you need to add, is very well correlated with the square of the surface tension increment of that salt. And the square obviously is what gets rid of the negative sign here, explaining what happens for both surface enhanced and surface depleted solutes. And so this indicates that essentially this phenomena is correct. But there's one really striking experiment which this Marucci or Gibbs-Marangoni stress really can't explain at all. And that goes back to a paper in the 90s in Nature published by Barry Ninham, my former advisor, and Rick Pashley and Vince Craig from the ANU. And what they did is they looked at the ion specificity of this phenomena. So they were trying to understand, do you see this for all different ions? And so they looked here at just the kind of fairly classic standard ions we think of, things like sodium chloride and the alkali halides, for example. And all of these ions, they categorized as alpha ions because they have positive surface tension increments. They all, we believe now, are repelled from the air-water surface, just like normal electrolyte solutions. And all of them have ticks because they all inhibit bubble coalescence. We see the same phenomena for all of them. What they then did is looked at a bunch of different other ions, more unusual ions. And what they saw was something quite remarkable. So they looked at ions such as the hydrogen ion or the perchlorate anion, right? And what they saw, interestingly, is that when you paired two of these ions with each other, you did get bubble-bubble coalescence inhibition. And you see that here in the bottom right-hand corner, those three ticks. And so it's believed that these electrolytes, these ions, which they call beta ions, are in fact enhanced at the air-water surface. And so it makes sense as to why these ions would inhibit bubble coalescence, because as I just explained, Marucci said this mechanism occurs for both depleted and enhanced ions. What's really interesting is that they showed that these ions, when they're paired with an ion of the other type, do not inhibit bubble coalescence at all. So if you take an alpha beta electrolyte or a beta alpha electrolyte, something like hydrochloric acid, you don't see this bubble coalescence inhibition phenomena at all. And that's really quite interesting and hard to explain. But I think I've come up with a relatively straightforward and simple explanation of what's going on here. And the basic idea here is that if you take something like hydrochloric acid, we know that that hydrogen ion will be attracted to the interface, will be enhanced at the air-water surface relative to bulk. In contrast, chloride will actually be depleted from the surface naturally because it likes to be in bulk water, has a positive surface tension increment normally. And this will actually create a charge separation. Whenever we have a separation of charge, we will have an electric field. So in this case, you'll get a positive charge at the surface and then a negative charge more deep into the liquid, and that will create an electric field pointing into bulk. And this electric field will then act to perturb the distribution of ions at the surface. It will push positive ions into bulk and attract the negative ions to the surface, cancelling out the natural propensity of those ions for the surface. And so this actually quite nicely explains why these alpha beta and beta alpha salts do not inhibit bubble coalescence, because their natural propensity for the interface has been cancelled out by the electric field created by that charge separation. And so obviously we need to quantitatively model this effect, and this is what I do in the preprint you can find here with more details if you're interested. The basic idea is we solve the Poisson-Boltzmann equation to calculate the surface potential, where the key input parameter is this G, this Gibbs absorption free energy of the ions to the surface. And we fit that to match their surface tension increments, and then we can predict the surface potentials and the surface densities of these ions and show that yes, we really can explain these ion-specific behavior of this phenomena. Alpha beta and beta alpha salts will not inhibit coalescence because they have a much weaker propensity for the interface.